Hello again, and welcome to our third and final part of Chapter 4. In this part, we will cover Newton's second and third laws of motion. In Part 1 of this chapter, we introduced the concept of force. In Part 2, we looked at Newton's first law of motion, and in this final part, 3, we will look at Newton's second law of motion and Newton's third law of motion. Let's begin with Newton's second law of motion. So consider a demonstration here. Suppose the student down here decides to push this heavy crate across the room by sliding it across the floor. Let's go ahead and watch an animation of what happens. Okay, so we saw that there's obviously a net force. We'll show it again a couple times here. You can watch it again. There's a net force, but the key thing here is, two things. One is the crate moves, okay? It's not at rest. But how would you describe the motion of the crate? Did it move at a constant speed? Think about this and watch the motion one more time and think about how you would describe the motion. Newton figured out what you just observed here. Net force causes acceleration. In other words, the crate that was being pushed by the student didn't just move at a constant speed, it sped up as she pushed it, as she continued to push it. Now, think about what might happen if we were to double the force. For example, what if we used two students pushing the crate instead of just the one? What do you think would happen to the acceleration? Well, you're right. The acceleration would increase. And how much? Well, it would actually double. So if we double the force, we would double the acceleration. And likewise, what would happen if we used three students and tripled the amount of force? Well, now we would triple the acceleration. So we can kind of show this mathematically using some symbols here. So we're going to show that a force F leads to an acceleration A, and then 2F, 2 times that force, would lead to an acceleration of 2A. And likewise, 3F would lead to an acceleration of 3A. So the idea here is that acceleration is proportional to the net force. So we can write this again mathematically by saying that A is proportional to, that's this symbol here, to the net force. So this is one of the key ideas of Newton's second law, is that a net force causes acceleration and the acceleration is proportional to the net force. Now there's something else though that we haven't considered yet, and that is, what is the effect of mass on the acceleration? So in other words, how would the acceleration of the crate change if the mass was doubled? Well, as you could probably guess, that if the mass was doubled, it would be harder to accelerate the crate, so the acceleration would be less. And it turns out that if we double the mass of the crate, we would end up with 1/2 the acceleration. Likewise, if we were to triple the mass of the crate and still have just this one student pushing it, the acceleration would now be 3 times smaller. In other words, the acceleration would be 1/3 of its original value. So what we would say here to summarize this rule here is that acceleration is inversely proportional to the mass of the object. So acceleration is proportional to 1 over the mass of the object. So in other words, the more massive, the less the acceleration is, and it is inversely proportional to the mass. So we can now put together these two concepts that we just learned about in the last 2 slides from our accelerating crate, and we can put it together to come up with Newton's second law of motion. So let's combine our 2 results that we just got from the last couple of slides. We learned that the acceleration is proportional to the net force, and the acceleration is proportional to 1 over the mass of the object. So combining these together, you can see that net force is going to be on top in the numerator, and mass, m, is going to be down below in the denominator. And so this is what Newton figured out. The acceleration of an object is equal to the net force on the object divided by the mass of the object. So Newton's second law is usually written without the fraction here. So to eliminate the fraction, we can just multiply both sides of this equation by m to get rid of the m down here. And this is the way that Newton's law is almost always written. It's written as F net equals ma. F equals ma. So notice that this is the net force acting on the object. Okay, not just any force, but we have to consider the net force acting on the object. M is, again, the mass of the object, and A is the acceleration of the object. So Newton's second law, F net equals ma, is arguably the most important and fundamental law in all of physics. We will be using it over and over, and we will be applying it to many, many different situations and problems. The law is important and fundamental because it describes why things move. Net force causes acceleration. This is cause and effect, okay? The net force is the cause and the effect is the acceleration of the object. And from a vector standpoint, net force is a vector. So whichever way the net force points, the acceleration will point in the same direction. So the object will accelerate in the direction that the net force is pushing it. One of the first applications of Newton's second law that we can do here is to use it to calculate the weight of an object. And this was a result that we actually learned about in part 2 of this chapter, but we're going to prove the result now. So suppose we take an object like a ball or an apple and we just drop it, we let it fall. Well, if we ignore wind resistance, then the only force acting on the object is its weight force pointing down. So according to Newton's second law, the net force on an object is equal to the mass of the object times its acceleration, F equals ma. Now, in this situation here, since we're ignoring drag or air resistance, which is safe to do because the apple's not falling that fast or that from that high up, then the only force on the apple is this weight. So the net force, F net, is just equal to the weight of the apple. So we have weight of the apple is equal to ma. But remember from chapters 2 and 3, we learned that for an object in free fall, all objects, no matter what their weight, fall with an acceleration equal to g, which is of course 9.8 meters per second squared. So we can replace this a here with g, and we end up with a simple result to calculate the weight of any object. W for weight is just equal to the mass times g, which is 9.8. So here are a couple real basic examples that use Newton's second law. In chapter 5, in the next lecture series, we will be looking at many, many more examples of using Newton's second law on more difficult and challenging problems. But let's start with some real easy ones here. So in this first problem, we have a 500 kilogram rocket is in deep space when all of a sudden it fires its engines and they have a thrust of 20,000 newtons. What is the rocket's acceleration? So this is just a simple application of F net equals ma. We are trying to solve for the acceleration of the rocket. So the acceleration is equal to the net force divided by the mass. So the net force on the rocket is 20,000 newtons. Notice we're in deep space, so there's no gravity, there's no weight, there's no normal force, and of course in deep space there's no wind resistance. So the only force acting on the rocket is the force of the engine thrust, which is given as 20,000 newtons. The mass of the rocket was given to us as 500 kilograms. So the acceleration is just 20,000 divided by 500. And the answer here is 40, okay? Notice that the force, we always want to make sure it's in units of newtons, and we want to make sure the mass is always in units of kilogram. Whenever we do that, we'll always come up with the proper units for our answer. So 20,000 divided by 500 is 40, And you can see the kilograms cancel out here, and we end up with meters per second squared, which are, of course, the correct units for acceleration. A second problem, what is the mass of a book if a net force of 10 newtons causes it to accelerate at 5 meters per second squared? So again, let's just use Newton's second law, F net equals ma, and this time we're going to solve for m, the mass of the book. So mass is just equal to net force divided by acceleration. So the net force is 10 newtons, and the acceleration was given to us as 5 meters per second squared. And so our answer is just 10 divided by 5, which is 2. Now, we don't really have to do this all the time, but if we recall that a newton is a kilogram meter per second squared, and we divide that by the acceleration, which has units of meters per second squared, you can see that the meters cancel and the second squareds cancel, and what we're left with is the kilograms, the unit of mass. We don't have to do all this unit gymnastics as long as we remember to always use kilograms for mass, newtons for force, and meters per second squared for acceleration. We know that our answer will come out in the proper units of kilograms. Let's now turn to Newton's third law of motion. Newton's third law has to do with the concept of force pairs. Newton realized that forces always come in pairs. In other words, you cannot have a force that exists by itself. It will always have a force pair associated with it. There are different ways to state Newton's third law. The one that you've maybe heard of is that for every action, there is an equal and opposite reaction. What this really means here is that for every action force, there is an equal and opposite reaction force. So before we talk about some of the specifics of Newton's third law and do problems and so forth, let's just get a sense for how to identify reaction forces for each of these examples shown here. So the first one, here's something that you can do right now while you're sitting at your desk or the table. Push your hand down on top of the tabletop or the desktop. So your hand is pushing on the desk. You can think of that as the action. What is the reaction? Well, one way to think of this is that if your hand is pushing on the desk, then your desk pushes back on your hand. Okay, and so the idea here is that you can't push on something without it pushing back on you. So another example, if you touch the wall in the room that you're in right now, the wall is also touching you. So it's impossible to touch something without it touching you. One kind of trick here to help figure out how to determine what the reaction force pair is just to take the sentence in real simple syntax here. So in other words, hand pushes desk, and just flip-flop the subject and the object here. So instead of we put hand over here and we take desk and put it in front here, so we end up with desk pushes hand. So you can use that same trick here for if you're pulling on a rope, what is the reaction force pair for that? Well, again, you can say that hand pulls rope, therefore rope pulls hand. So when you grab a rope that's, say, tied to something like a tree, and you pull on that rope, well, the rope is going to pull back on you with an equal and opposite amount of force. How about throwing a ball? What is the reaction force for throwing a ball? Well, what you're doing with the ball is basically your hand is pushing the ball. So the ball is pushing back on your hand with an equal and opposite force. And it's not super obvious, when you're throwing a light ball, like a tennis ball or something like that. But if you try to throw something heavier, like a heavy rock, or say, a shot put or a bowling ball, well, you're going to feel a lot of force pushing back on your hand as you try to push the ball forward. What about if you were to push on a spring? Well, in this case, the spring will push back on you. How about this one here? A magnet pulls an iron bar. What is the reaction force for this one? Well, the iron bar is going to also pull on the magnet. So when we say a magnet attracts iron, really what is the proper way to say this is a magnet and iron are attracted to each other. Now the last one, this one's a little trickier. Think about dropping a ball. What are the forces involved in the Newton's third law force pair? In other words, what's the action and what's the reaction? So think about this if you want for a little bit, maybe pause the video and we'll talk about it on the next slide. All right, so just to recap Newton's third law of motion, for every action there is an equal and opposite reaction. Forces always come in pairs. Each force in the pair acts on a different body. So Newton's third law is basically saying that what a force really is, it's an interaction between two objects. So let's consider our the example on the last slide where we're taking a ball and just dropping it to the floor. Okay, so here's our ball. Well, we know that the ball falls to the earth because of the force of gravity. Gravity is pulling the ball down to the earth. So this is the force of the earth on the ball. So what is the Newton's third law force pair? Well, remember, all we do is switch these two words here. So the force pair is the force of the ball on the earth, and it acts in the opposite direction. So what actually happens here when you drop something, like a ball or a rock or a pencil, anything, is the object and the earth are attracted to each other. The object falls downward towards the earth because of the force of gravity. The earth, though, feels an equal and opposite force pulling it upwards. So the question is, why don't the ball and the earth fly together and meet somewhere in the middle? Well, remember Newton's second law, F equals ma. Acceleration has to do not only with force, remember the forces here are equal, but it has to do with mass. So the ball obviously has a very small mass compared to the earth. The ball accelerates at 9.8 meters per second as it falls down. The earth, because its mass is so enormous, does accelerate upward, but the acceleration is minuscule. In fact, it's infinitesimal. It would be, impossible to measure, but in theory, the earth does accelerate upward a tiny, tiny bit. So one question that comes up here, and you can maybe challenge your friends with this one, is can you move the earth? And the answer is yes. Just drop your keys to the floor. And if your friends don't believe you, tell them Isaac Newton said so. There's a classic physics problem called the horse and the wagon paradox, or sometimes it's called the horse and cart problem. It's kind of an interesting take on Newton's second and third laws. And like a lot of paradoxes in physics, they seem like a paradox until they're properly explained. So here's a situation. We've got a cart here with Farmer Bob sitting in the cart, and he's got the cart hitched up to his trusty horse here. And the farmer says, "Come on, old horse, get going and pull this wagon." Well, the horse, who is actually very intelligent and can talk, says, "I took physics class. Newton's third law says that if I pull on the wagon must pull on me with an equal and opposite force." And the farmer says, "So what? Let's go." But the horse says, "But since the two forces are equal and opposite, they cancel each other, meaning no net force." So in other words, the horse is pulling on the cart with this force here, but the cart or the wagon has to pull back on the horse because of Newton's third law. And remember that these two forces have to be equal in magnitude, same number of newtons of force, and they point obviously in opposite directions. So there is no net force then. And the horse says, with no net force on the horse-wagon system, Newton's first law says that an object at rest must stay at rest. Furthermore, the horse says, Newton's second law says that with no net force, there can be no acceleration, so we can never start moving. So is the horse correct? since these two forces are equal and opposite, is it impossible for a horse to pull a cart? See if you can figure out the solution to this seemingly paradoxical situation. Well, we can resolve the paradox by realizing that our horse is very smart, but he forgot something. He forgot about friction. The way the horse walks, or anybody walks for that matter, is that he pushes backwards on the ground. So the horse is pushing his hooves against the ground backwards. But the ground then, by Newton's third law, pushes the horse forwards. So when you walk, think about this. What you're really doing is you're pushing backwards with your feet on the ground, and the ground therefore is pushing your feet forwards, and that's what makes you actually move. So the horse and the wagon here, the free body diagram, we've got weight down and normal force up, of course, but these two forces, internal forces here, the force of the horse on the wagon and the force of the wagon on the horse, they cancel each other. The only force on our wagon and horse system here, there's one net force pushing forward, and that's the force of the ground, which propels them forward as the horse pushes off on the ground. Newton's third law is also used to explain how scales work. Scales rely on Newton's three laws of motion. So when you're standing at rest on a scale to weigh yourself, Newton's first law says there's no net force on you. Of course, you're at rest. Thus, your weight force, which is down, is equal to the scale's normal force pushing up on you. Now, Newton's third law says that the normal force of the scale on your body is equal and opposite to the force of your body on the scale. Therefore, the scale feels and measures your weight. Likewise with the spring scale, when we hang something here, all right, this object is at rest, so its weight force down is balanced by the tension force of this little cable here that hooks onto the mass. So the tension in the cable is equal to the weight of this object. But of course, this weight, this cable here, which is pulling up on this object, is also pulling down on the scale with the same amount of force, and so the scale reads that tension, which is equal to the weight of the object. Well, our last slide here in this chapter 4 is on a concept called apparent weight. We'll compare and contrast this with actual weight. So we know that weight is the force of gravity acting on an object, and a person's weight is always constant, assuming that the gravity in your environment is constant. Now there's something else called apparent weight, which is how heavy you feel due to the normal force pushing against your body. So apparent weight is defined as the normal force pressing against your body. So let's look at three different situations here. We've got a man inside of an elevator, and he's standing on a bathroom scale. All right, now in this first picture here, the elevator is not moving at all. Okay, so let's just assume it's at rest. So we know that the weight force of the man pulling downward is equal to the normal force of the man pushing upwards on his feet. Therefore, there is no net force on the man. Therefore, he is not accelerating. Okay, now this also applies if the elevator is moving at a constant speed. If the elevator is going upwards or downwards at a constant speed, this situation holds. There is no acceleration. Therefore, the normal force is equal to the weight of the man. And so let's say this man weighs 150 pounds. Well, then the scale will accurately read his true weight, which is 150 pounds. Now let's look at this picture here. In this picture, the elevator is accelerating upward. You can see the acceleration arrow shown here. So the elevator is starting to move, from the ground floor going up, and it's picking up speed. It's accelerating. Well, we know that for something to be accelerating, we have to have a net force. This is Newton's second law. So there must be a net force on this man. Well, again, there are only two forces on this man. There is his weight pulling down, and there's the normal force from what he's standing on, the scale, pushing upward. So his weight does not change. Remember, weight is equal to mg, which is his mass times 9.8. What does change is the normal force. The normal force in this situation must be greater than his weight so that there is a net force pushing him upward. This net force is what makes him accelerate upwards with the elevator. So in this case, the scale might read something like 180 pounds, right? The scale is going to read heavier than his true weight. The scale is reading the normal force, how much the man and the scale are pushing on each other. And remember, the normal force has to be greater than his true weight in this situation. So you might notice this the next time you're in an elevator. When the elevator starts going upwards, you will notice that just for a brief, maybe a second or two, you'll feel slightly heavier. You'll feel a little bit of extra force on your legs due to this increased normal force. Your apparent weight has momentarily increased. Now, the opposite happens when the elevator is accelerating downward. So imagine you're at the top floor of a building and you press, the first floor on the button, so the elevator starts accelerating downward. So now, in order for you to accelerate downward with the elevator, there must be a net force pointing downward. That's only possible if the normal force is smaller than your weight. Again, remember, your true weight does not change. It's equal to mg, but the normal force does change. So in this case, your normal force is actually less than your weight. So in this case, the scale might read something like 120 pounds instead of your true weight, which is 150 pounds. And you'll feel this too. When the elevator accelerates downward, you'll have that momentary feeling where you're falling and you feel a little bit lighter and you kind of feel your stomach turn just a little bit as well. All right, so that wraps up chapter 4 on Newton's laws of motion and forces. That's it for this chapter, and we'll see you next time.